All right, the unit that we will begin today, continuing Unit 9, we are doing Topic 3, Growth and Decay Models. So what are some situations that you can model with an exponential growth and then with an exponential decay model? So this formula right here is actually two different formulas in one. So when a real life quantity increases or decreases by a fixed percent each year, the amount in of the quantity after t years can be modeled by these two equations. A is your initial amount. So that's your starting number, whatever you start with, however many you start with. The R here is your rate of increase or decrease, and it's usually given as a percent, but you need to convert it to a decimal. The exponent is your time, and usually it's in years, but it can be other increments or other time periods. Now, from last week, we talked about the base. This entire thing would be your base, and it's either your growth or decay factor. It's the entire base. To get the R value, it's either adding or subtracting 1 to it. To 1, you add for above 1 growth, and then to get the decay, you need it to be less than 1, so you would subtract. All right, and then N or Y, whatever you want to call this, this is your total amount. This is the amount you have after t years. So that's usually what we're trying to find. All right, so I'll do example 1, and then you can do example 2 with your group, checking your answers. I'll do example 3, and then you can do example 4 with your group. So looking at 1, so I'll do these 3, and then I'll move it to the bottom ones because we're going to need to look at the graph for that one. So in the last 12 years, an initial population of 38 buffalo in a state park grew about 7%. So first, we want to know, is it a growth or decay? So this thing says that it grew, so I know it has to be a growth, which means I want to use the growth model, y equals a times 1 plus r to the t, not the decay one. All right, A is your initial amount. So how many you start with? We started with 38 buffalo. So 38 is going to be the A. And for my percentage, 7% as a decimal, we would just move it back twice, multiplying it by 100, makes it 0.07. So making our equation, y equals, or n equals, either way, 38 is the initial population, and we do 1 plus, since it's growth. R is 0.07, so we want to add 0.07 to it. And because it's asking for an equation, we're going to leave t as t. We'll plug in a number for t down here, but right here is just the equation. So our equation is 38 times 1.07 to the t power. Now for B and C, we're actually going to use the model to answer some questions. So for part B, we want to use this equation to estimate how many buffalo were in the state park after 7 years. 7 is giving us time, so we're going to plug in 7 for the exponent. So 38 times 1.07 to the 7th power. Now grab your calculators, and we want to do, just enter that in the calculator, 38 times 1.07 to the 7th power. And we get that decimal, 61.096, but we're talking about buffalo here, so we just round it to the nearest one. We say approximately 61 buffalo. All right, so y, unless it's cents, I mean, if it's money, we can round it to 2 decimal places. But when we're talking about population, we'll round it to the nearest whole number. All right, so part C, we're going to need to use our calculator to find So use the graphing calculator to sketch the graph and estimate the year when there were about 53 buffalo. So what we're going to do here is we're going to take our equation and plug it into y1. So our equation was 38 times 1.07 to the x. And in y2, we want to plug in the number that it wants. So here we plug in 53. So going to the calculator, and the y equals, we're going to do 38 times 1.07 to the x power. And then here, we're going to do 53. Oops, 53. Now, I give you the graph over here, not because I need exact points, but because this actually gives you the window you want to use. So if you go to window, the number here, this is your x-axis. So this is your x minimum. You can't even see that. So x minimum here. So x min. And then the number over here is your x max. And scale is what it counts by. So I want to start at 0, go to 10, count by ones. And then the y min is here. So y min. And then the y max is up here. So then we go 0 to 100. If we go one above it, 100. And what is this one counting by? This one's counting by 20s. So I go by 20s. The scale is 20s. And then if we graph it, I mean, I'm just going to sketch that out. I'm not going to make it exact. But there's our 53. So 20, 40, 50s in the middle. Kind of a horizontal line there. And then our equation starts off at 38, close to 40. And then it's going to go up. Okay. So we're trying to find this point right here. Now this one's not exact. We're going to find it exactly over here. So if we remember how to find the intersection in the calculator, I'm going to write it down here. You do second, trace, and then it's number 5 to calculate the intersect. So second trace number 5 is the intersect one. And then we can just do enter, because they each only have one piece. So enter 3 times. So enter times 3. So then we get that x is 4.917. I'll just put 4.92. This is years. Now, again, we can round it to 5 years. That would be fine. But if we can find the exact, we can always round. But just because you can round doesn't mean you can find the exact. So I want to practice finding the exact here. And then if it says round to whatever the decimal is, we just round to that number. All right, so go ahead and read number 2. Figure out those numbers and make your equation. And then I'll show the screen in just a second that has all those answers. All right, so checking your answers. Here we know it's growth increases. A value is the 2573, and then the 0.92 is the R value. So here's your function. Plugging in the 7 for the 7th year from 1996 to 2003, hit 7. So then we get the 247,484. This one, I know is a little hard to tell what the increments were. So the min and the max on the X should have been 0 to 10. Because, again, you don't want to go too far past 10. And this one on the Y-axis, it goes all the way to 200,000 by, it looks like 50,000s. If it doesn't give you the graph, then the way that you figure it out is you want it to be at least this big, but a little bit more to see the growth, how far it grows. So just fix your window there and then find your intersection. For this one, the intersection ends up being, so if you do second trace number 5, enter. The exact value for the intersection here is time equals 5.95 years. But then we can round that in the end to 6. But again, being exact first and then rounding is important. We will eventually learn how to solve these, but those take logarithms. All right, so now moving to the bottom part. So example number 3, again, I'll do 3 with you, and then you can work with your group on number 4. So for number 3, a new television costs $1,200. The value of the TV decreases by 21% each year. So because it decreases, that tells me that it's going to be a decay graph. And for decay, we want to use the formula y equals a times 1 minus r to the t. So the a value is the initial amount that you paid for. So a new TV is the 1,200. And the r value is your rate of decrease. So the 21% as a decimal would be 0.21. And then we just plug it in. So y equals a is 1,200. And we do 1 minus, because it's decreasing, 0.21. And we raise that to the t power. So when you write a model, when it just asks for model, you leave x and y there. When it asks you for a specific value, then you can plug it in. So we get 1,200 times subtracting, not adding. 1 minus 0.21 is 0.79 to the t. All right, and then estimate the value after 2 years. So here 2 is giving us time. So we want to plug in 2 into the function that we made. So 1,200 times 0.79 squared. And then we grab our calculator and we go ahead and square this. So clear that. 1,200, I don't need the parentheses there. 1,200 times 0.79 to the second power is, and this is in dollars because it's the value, so $748.92. So again, find the exact. After you find the exact, then you can go back and round it to maybe 750, but make sure you can find the exact first. All right, estimate when the value will be $300. So again, the 300 here is giving me the y value. So this is where I use the graph and plug my function into y1. Make sure you do the one with the x. So 1,200 times 0.79 to the x power. Then we're going to use our window to get the rest. Let me clear this stuff. So 1,200 times 0.79 to the x power. And then in y2, we put the 300 that it wants. Now, if you go to your window, it's still 0 to 10. We don't go very far past 10. We'll get to that in a second. But the y values this time, so go to your y min, still at 0, but the max would be 1,400. And this one's counting by 200s. So when you graph it, you should see a pretty good graph in this window. So here's the 300 line, kind of in the middle there. Nope, that's not in the middle. So draw your horizontal line at 300. Pretend that's horizontal. And then you draw your other graph decaying. So this is where it starts. So it starts at 1,200, and then it decays from there. So again, what we're trying to find is where they intersect. So second trace number 5, and then enter, gives me that t is 5.88 years, which again, we would round it to 6 if we were just, because it says estimate, But if you can find the exact, you can always estimate. But it doesn't work the other way around. If you estimate, you can't always find the exact. All right, and then part D, it's asking us to find it after 10 or 15 years. So you can plug in 15 for the exponent, but since we already have it right here in the calculator, I'm just going to look at the table. So go to where it's 15, and it says that the price would be $34.96. Then it asks, is it reasonable? So the reasonableness is asking about the situation. So is it reasonable for us to pay $35 for a TV that's 15 years old? And usually the answer to this is no. Technology changes so fast that in 15 years it's going to be a different kind of TV that you're going to be watching. And the old one's probably not even going to work on whatever program they have. Just like now, you won't watch the same TV we watched 15 years ago. So usually we don't estimate that far out. So the X's are always going to be within 10 years for these predicting problems because of something called extrapolation. So right here, extrapolation is the process of estimating beyond the original data. So the original data is usually 0 to 5, 0 to 10 maybe, but anything outside of that is subject to uncertainty and a risk of higher of meaningless results. So I could ask you what's the price in 100 years, and the function will tell you the answer, but that really is not going to mean anything because it won't exist or we won't exist. So we don't estimate these things outside of a certain range. Usually that range is 10. All right, so go ahead with your group, do example number 4, and then I'll come back and show you the answers before we get to the bottom part. All right, so checking your answers for number 4. So we should get the formula 4200 times 0.9 to the t. It's decay because it decreases, and 1 minus 0.10 is 0.9 for the base for the decay factor. Plugging in 3, you get that it's $3,061.80. And then looking at the graph over here, again, we can't extrapolate, so 0 to 10 is usually the x value. And then this one, the y-intercept is 4,200. So you can kind of interpret that that's 5,000. So they go by thousands here. So if we were to graph the 2,000 mark, right here, horizontal line at 2,000. And then we would just look at our y equals. So in y1, we type in the 4,200 times 0.9 to the x. And in y2, we type in our 2,000 with this window, 0 to 10, 0 to 5,000. Second trace number 5, enter, enter, enter. Gives us that time is 4.92 years. Which again, we would round it to 5, probably in answer choices. I won't ask you for exact until we get to solving. But you can get solving right now, and then we can find the algebraic part later. We can estimate it once we know how to get the exact. All right, the other 3, they're very short. They're very similar to growth and decay. So there's a doubling formula, there's a tripling formula, and then there's a half-life formula. So notice a lot of these are the same values. The A is your initial amount. We don't have an R value because for doubling, the base is 2. Tripling, the base is 3. And half-life, the base is half. The part that is different is the P value. P is the period that it takes for the number to triple or to double or to cut in half. So P for all of these times for the exponent is how long does it take to double? How long does it take to triple, and how long does it take to be cut in half? All right, so if we look at example 5, it says a population of bacteria doubles every 3 days. So I know I'm using the first one here. So N equals, if the initial population is 1,500, so the initial is your A value, so A is 1,500. I know it's a doubling, so I'm going to multiply by 2 to the T divided by P. So right here, how many bacteria are in the colony after 3 weeks? So the 3 weeks is what it's asking us. This is the time. But we need these units to be the same. So if this is in weeks and that's in days, we need to convert this to days because it's easier than converting that to weeks. So 3 weeks is 21 days. So we're going to do 21 is the T divided by the period is how long it takes to double, and it takes 3 days to double. So this would be your period. So in the calculator, we're doing, so clear all this, 1,500 times 2 to the 21 divided by 3 is just 7. So then there are 192,000 bacteria. All right, so here it's actually 100% growth is what the R value would be, because 1 plus 1 is 2. So this, if you wanted to get the R, you could, but when it doubles, that's 100% that it's growing. All right, for example 6, a culture of bacteria triples every 8 hours. If there are 100 bacteria now, how many will there be in 18 hours? All right, so let's look what we need. So first of all, we're doing the tripling one, so we're using the second equation. N equals the initial amount is 100 bacteria. So 100 times triples has a base of 3. And the exponent, we do the time that we want divided by the period. So the time that we want is 18 hours. So 18 is the numerator. But then we divide that by the period, which in this case is the 8 hours here. So 8 goes in the denominator. I mean, you can reduce this and simplify it, but since we're going to type it in the calculator anyway, we can just leave that as the exponent. 100 times 3 to the 18 over 8. And we get this number for N, but we're talking about bacteria, so we can just round it to the nearest whole number. So 1,184 bacteria. Now, half-life, you see half-life and radioactive decay. So if you put something out on the ground, how long does it take for the substance to reach half the amount that it started with? So that's when we use half-life, is for decay. So here it says the half-life of carbon-14 is 5,730 years. A plant contains 100 grams of carbon-14. How much carbon is left after 200 years? So because it says half, I know I'm going to use this one. N equals, how much did I start with? So I started with 100 grams. So 100 goes here. And we're talking about half-life. So half. And the exponent, the time that I want, is 2,000 years. So we do 2,000 divided by the period, which is 5,730. Now, if you've heard of carbon dating, the reason they use carbon to figure out, how old something is, like a fossil or something that they find, is because it takes so long for it to decay. It takes, for half of the stuff to decay, it takes 5,000 years. So more than 5,000 years. So there's still stuff left. Depending on how much stuff is left, we'll tell you approximately how old it is. So then we just put this into the calculator. Times 1/2 to the, and then we just divide these. 2,000 divided by 5730. So N equals, and we can't have decimals here because we're talking about grams. So we can say 78.5 grams of carbon. So again, it hasn't even lost that much. It's been sitting for 2,000 years, but it hasn't lost much of the carbon that it started with. All right, so those are just special cases. Most of the time it's growth or decay. So tomorrow we'll do the interest rate ones, and then we'll be done with the modeling. So now you can work on your homework or get the new homework.